George,
Aye, Mr. Newton.
don't lock up. I'm expecting Mr. Chambers.
Aye, Mr. Newton.
And what I am telling you, Mr. Newton, has been learnt by experience. Pig iron is scarce, especially of good quality iron. We must start in a small way, buying our iron and casting it ourselves here in Sheffield. And then, when we can, build furnaces and smelt our own iron.
I believe you're right, Mr. Chambers, and I fully believe that this is only the beginning of this start in iron. Most likely in our lifetime, we shall see a great deal more of this metal used.
And if we anticipate, we shall profit.
Not too much anticipation, Mr. Chambers. Let us proceed with the present. It has been agreed that I sell my interest in this business to my partner, Mr. Hodgson, and we begin in the iron foundry business at a place selected by us at Snow Hill. Under certain conditions known to us both, I provide the money.
And I, the practical experience. But the price of pig iron is monstrous. What with war with France and the demand for cannon, prices are soaring. No one can tell where it will end.
It might put us out of business.
Yes, or show the way to greater prosperity. We must make an important decision, Mr. Newton, to erect furnaces immediately and smelt our own iron. During the next day or two, we must select a suitable site in the neighborhood.
But these premises, we are bound to them.
They can bring in the iron from the furnaces in carts and cast it here. Now there's Thorncliffe, that's a suitable place.
We must look for quantity and quality.
And the last of the two is, in my opinion, the more important. I am certain that we shall find out at Thorncliffe that the clay-bound stone will give iron of the very best quality.
What about fuel?
Coal?
Are you sure coal is suitable for the purpose, Mr. Chambers?
Absolutely. In a few years, there will be no more charcoal used in smelting iron. For one thing, the supplies of wood are failing. And besides, I am sure that coal is more suitable.
Right, Mr. Chambers? If you're satisfied with Thorncliffe, I am.
Then we must do something straight away. Our friend, Mr. Swallow of Chapeltown, Paris, is considering buying that very piece of land we have decided on.
We'll ride over to Thorncliffe tomorrow and settle the matter with Lord Fitzwilliam.
And so the firm of Newton Chambers was founded. It prospered, first in a small way, and then, in the midst of a new industrial world, it grew big. But the spirit of its founders lives on in the company. It has moved with the times in all enterprise, yet it has never departed from the traditions born 150 years ago. Mr. Newton and Mr. Chambers went out into the countryside to find ironstone. They found it, and they also found coal, the real value of which they could not possibly estimate. Today, the Newton Chambers Company consists of a group of large enterprises, all of which are based upon the excellent supply of coal which the founders of the company so happily discovered. Five collieries are at present operated by the company. Many grades of coal are produced: coal for the home, coal for industry, and coal for export. This is Rockingham Colliery, the most recently opened. It is equipped for up-to-date mechanized mining and has the most modern coal grading and cleaning plant. The pithead is situated some 5 miles from the main works, and a large proportion of the coal output is conveyed by a system of aerial ropeways and conveyors to the Thorncliffe coal distillation plant at the main works. The coal arrives by aerial ropeway, and after having been specially pulverized, is automatically fed by a moving conveyor belt into the top of the bunker from which this photograph was taken. The plant is one of the largest in this country. It is here that coal is heated and made to yield up its chemicals, amongst them being benzol, ammonia, coal gas, coke, and a valuable range of oils. The high twin towers are scrubbers, where the benzol is being cleaned for British motor fuel. The ammonia is transformed into a chemical fertilizer, which is exported in large quantities to all parts of the world. 8 million cubic feet of coal gas are pumped from this plant daily by special pipeline to Sheffield for public consumption, the remainder being used to heat the ovens themselves or for power purposes. Of the coke, some is sold in the open market and some conveyed back to the company's blast furnaces. The coal oils go to the chemical works, where they are treated and transformed into finished products. Nothing is wasted. Here we have the tops of the ovens themselves. There are 59 of these ovens, and each is charged in turn with coal, which is baked at carefully controlled temperatures. The charging is done by means of traveling hoppers, which measure out the correct quantity for each oven. As soon as all the volatile constituents have been extracted from the coal in any individual oven, a door situated at one end of it is unsealed and removed, and a mechanical ram pushes the hot coke out. A travelling car is waiting to collect this coke at the other end of the oven. The ovens are self-heating, since, as we have already explained, part of the gas generated from the coal is brought back to them and used to keep up the temperature. Thus the process is continuous and the highest degree of efficiency is always maintained. The hot coke is brought in by a travelling car under a quenching tower, where it is quenched by a fall of 15 tons of water. The water is carried away in the form of a large cloud of steam. The travelling car then moves back and discharges the coke onto an inclined bank where it cools before being conveyed away by a moving belt. Aerial ropeways take much of this coke to the company's blast furnaces, and the balance is sold and dispatched by rail for use as coke fuel. The main works occupy essentially the same site as that selected by Newton and Chambers a century and a half ago. Iron has actually been smelted on this site since Roman times. The expansion of the works has been constant. Old plant is continually giving place to new, and the process of change is unremitting. The present blast furnace, with its elaborate attendant plant, some of which is seen here, was constructed by the company in the shops at Thorncliffe and was first put to blast in 1925. It consumes iron ore, coke, and limestone. The coke coming from the ovens which we have just seen. Iron ore and limestone are brought by train and are discharged into bunkers situated just behind the furnace. The materials are hauled to the top of the furnace by a double skip hoist, electrically operated and controlled from a cabin below. In this way, 500 tons of raw materials are fed into the furnace daily to allay its incessant hunger. The furnace discharges every 6 hours 35 tons of molten iron, which is cast in sand molds called pigs, specially prepared to receive it. It works day and night, in all conditions, rain or shine, without interruption for stretches of 5 years or more. This continuity of operation is most important, for should the furnace be allowed to go out through lack of fuel or any other cause, it would cost many thousands of pounds and would entail many months of labor to put it into blast again. Sometimes the iron runs calmly and smoothly into the waiting pig beds, and again, sometimes it doesn't. Note the quickness and skill of the men engaged on this work and their ability to stand up to the immense heat generated by the hot iron. In the meanwhile, in the pattern shops, exquisitely made wooden patterns from which the sand is moulded are taking shape. Skilled craftsmanship and most modern machinery combines to produce work of the greatest accuracy. In the foundry itself, the pig iron is re-smelted in smaller furnaces, or cupolas, preparatory to being used for casting. It is then poured from the cupolas into ladles, and is conveyed in these by electric cars to the various casting points in the foundry, as required. The shops, as you see, cover a very large area indeed. We are now passing from one end of the foundry to the other. At this end, we have heavy iron castings, such as slag ladles for steel works, tank plates, castings for coke oven plant, gas works plant, steel works plant. In fact, all kinds of castings associated with the general engineering activities of the company. This foundry is one of the largest jobbing iron foundries in the country. It is light and airy. Through the far end can be seen the woods and grassy slopes which form its immediate surroundings. Working conditions here are in striking contrast to those which generally prevail in towns, and working conditions have much to do with quality in the finished product and with economical production. Time is too short for us to show you the entire foundry, but it extends to large light casting sheds which are devoted to the production of all types of castings for the building trade, together with the latest types of cooking stoves and grates used in many of the housing schemes all over the country. It has been said that Newton Chambers can produce in these shops anything from a rain pipe to a floating dock. The making of sand molds for tank plates is especially interesting, for the sand mixture is here propelled with great force from a sand slinger, which packs it down firmly around the pattern and so saves all the time of hand molding. These shops are equipped with the latest types of sand slinging machinery, together with up-to-date molding and sand preparation plant. The greatest care must be taken in the pouring of the molten metal, otherwise the finished casting may be faulty. These men are casting tank plates for large brewery storage tanks. In the machine shop, accurate finish is ensured by the latest types of machine tools. This is the latest type of Perns-Richards horizontal borer. It carries out every kind of boring, facing and milling with the greatest degree of accuracy. Here is a man at work on one of the many lathes in the shop. It is a counterpart of many others in use, larger and smaller than itself. This machine is a small, modern, high-speed shaper of the latest type. And here, a modern slotting machine, working on a section of one of the company's benzol scrubbers. 20 or more of these sections are assembled into a high tower. This modern planing machine, one of a battery of 6, is at work machining a roller gear frame for a Midland steelworks. The drilling equipment in this shop is of the very latest type. Here we have a typical power drill at work on another section of a gasworks scrubber. We now pass to the structural steel shops, where steel manufactured parts are assembled into a variety of large structures: gas holders, steel tanks, railway bridges, steelworks equipment, coke oven machinery, blast furnace plant, and all structural work associated with heavy engineering. Independent electric drive of the latest pattern is in use throughout these shops. It is only by the installation of the most modern machine tool equipment, by the employment and training of the most skilled labor, coupled with unusual conditions of lighting, flooring, and layout, that the work for which Newton Chambers has long been famous is maintained at such a favorable competitive standard. Here is a rotary shear, which cuts steel plates on a curve with perfect accuracy, and as easily as if it were made of cardboard. And here are plate bending rollers capable of bending 1¼ inch plates to any required radius. This is electric arc welding on a fractional distillation column for a large chemical plant. The company is tending towards a greater use of welding in construction. Here's an interesting machine. It's an oxy-coal gas cutter which automatically cuts the thickest circular tank tops at the rate of a foot a minute, making an unbelievably clean cut.
And now let us return to the coal oils, which were obtained from the coal distillation plant. It is time for us to see what happens to these oils, which are the raw material of many of the company's products. Let us first see a simple laboratory illustration of what happens to the coal in the distillation process. Here we have a test tube filled with crushed coal. We place a flame under it, and very soon coal gas, with some ammonia, are given off, whilst a thick deposit forms in the tube. This deposit, unpleasant though it appears, is made up of a range of important recoverable products. Every year new derivatives of it are made, and the public today have to thank it for scores of commodities, as widely varied as dyes and tar macadam, motor spirit and germicide. All these are derived from the volatile part of the coal, and after they have been driven off, coke is left behind. Here you see the coke from the tube. In the early days of coal distillation, this test tube experiment was repeated in beehive ovens, and the oils were collected in barrels. Their value was not at first realized, and they were used for lubricating wagon wheels, or thrown away. Later, they found a number of rough uses, and little by little their value became known. These same oils, obtained now from the modern distillation plant which we have already seen, are carefully collected and transported to the company's chemical works, where they are separated from pitch, tar, naphthalene, and other products. After separation, they are repeatedly distilled and refined. This is a general view of the chemical works where all this is done. The works occupy the same site as that on which Izel oil was originally produced 40 years ago. Pitch is one of the first products to be removed from the coal oils. It is here seen in the molten state, being pumped from a 10-ton still into the pitch beds, where it cools and hardens. There is a large market for pitch abroad, especially in France. It is hacked out in as large lumps as possible to prevent waste in transit, and is loaded direct onto rail wagons on a siding nearby. The French railways use it to combine with poor quality coal for making briquettes, which are used for fueling locomotives. Similar briquettes were used as a domestic fuel in England during the war. Duroid, the well-known non-skid road surface, is produced in large quantities. It is filled and loaded into rail wagons, in which it is dispatched all over the country in order to make safe and durable roads for our ever-increasing road traffic. It is interesting to recall that the company foresaw many years ago the coming demand for the non-skid road surface, and after much careful research introduced this product, Duroid. And now finally we come to Izel. This still is carrying out one step in the long and complicated refining process which results in Izel oil. And here we see the Izel oil coming through. It is stored in tanks until required. Samples of all products at all stages of production are taken very frequently for the purpose of laboratory control. Here a sample of oil is being taken, and it is immediately sent to the laboratory by a girl messenger. By the maintenance of an organized flow of samples between works and laboratories, a close check is kept on all works' progress. Chemists are continually carrying out tests on all samples: coal itself, pitch, duroid, and all fractions of oils, including the finished Isale oil, undergo the same severe examination. Hundreds of tests are made daily, so that the high standard of the company's products may be maintained. Work on the chemical side of the company is not surrounded by the same atmosphere of size and movement as that which marks the ironworks or the collieries, for its processes are silent and intangible, many of them invisible, yet its significance is beyond ordinary assessment, and its field of influence almost unbounded. New developments in British industry have come about as a result of the successful researches and the vision of Thorncliffe chemists. New products have been discovered, new uses have been found for old products, and new markets have been opened all over the world. It is the policy of the firm to concentrate upon substances obtained from coal distillation, and this field is so unbounded that still further discoveries undoubtedly lie ahead. These developments have brought to Newton Chambers and Company a worldwide reputation as experts on the chemistry of coal. A wide international service has grown up, best known probably in connection with the famous Isale products, and is now at the disposal of industries and governments and the professions everywhere. Work done in the bacteriological section of the laboratories links directly with that of the medical specialist and the field mycologist. Actual disease germs are used in testing antiseptic products at various stages of refinement. It is by such tests that Isale, in its finished state, which is after 9 successive refinings, is standardized to a germicidal strength 20 times that of carbolic acid, and is guaranteed, even when diluted 1,000 times, to kill virulent typhoid germs in 5 minutes. Here we see Isale and a black disinfectant each being added to pure water. They both mix well. But now the same test, under more practical conditions of disinfection, where water is almost always polluted. Isale mixes perfectly, whereas the black disinfectant does not. Even under ideal conditions, the black disinfectant has only a fraction of Isale's power, but under practical conditions, it does not mix at all. We examine the emulsion more closely in the laboratory under the eye of the micro camera. We will see actual Isale emulsion magnified many thousands of times. The movement of the small globules in the emulsion is what is known as Brownian movement. The tiny germicidal particles of Isale constantly bombard any germs with which they come into contact. We will see the fluid magnified to the same extent in which a single organism is visible. It can just be discerned moving up the center of the screen from the bottom, a minute, light-colored, worm-like shape. Now a drop of Isale solution is added to the solution on the slide. The Isale solution will be seen to float across the screen, and it is possible to compare the size of the Isale globules with that of the germ which they are attacking. They are very much smaller than the germ which they are to kill, and for this reason are more effective in their action against it.
Before Isale is dispatched in bulk, a final test of the product is taken to enable the laboratories to make a positive check on its germicidal strength. A sample for this purpose is taken just before the containers are filled. The small bottles of the germicide for individual use are filled semi-automatically, and the same check is taken on quality before filling is started. Here we see the filling of bottles by means of a vacuum filler. The fluid in this case is not Isale, but another type of disinfectant made from coal oil. The bottles are capped by a machine which can deal with several thousand every hour. A moving conveyor system carries them from one operation to the next. The labeling machine is designed to operate with an almost human feeling for the fragile bottle and its liquid contents. Here we have a sample batch of containers for dispatch. And now the order board for a day. By rail, road and sea, Isel goes to its customers in every part of the world. Here we have a consignment leaving for Shanghai. Tomorrow it may be Colombo or Cape Town. Abroad, even more than in England, health depends upon efficient disinfection. It is therefore with a heavy sense of responsibility that laboratory control is maintained throughout Isel manufacture. From the gold mines of South Africa and the rubber plantations of Malaya to John Citizen's bathroom in Britain, Isel is known as the most powerful, safest, and most reliable germicide obtainable. This one product of the Newton Chambers Company typifies its work as a whole and has established a reputation which it enjoys not only at home but throughout the world.